Okay, third video, we're going to have a video on residual plots. So make sure you have either your calculator or Desmos. Again, I'm going to try to do both. We'll try to do it fairly quickly. So we're going to examine these burgers. So if you would pause your video, take a moment to type these in. I'm going to type them into Desmos. I already have them, I believe, in my calculator here. So if you're doing the Inspire calculator, you name them X and Y, you type them into two lists, type them in if you're familiar with your calculator. If you're not familiar with Desmos, again, here we go on Desmos. I'm going to type these in. So we're going to click the plus sign. We're going to add a table. It's already got an X and a Y in there. I'm going to have to go back and forth a little bit. Okay, so we've got the amount of fat, and now we'll go with the calories. 410, 580, 590, 570, 640, 680, and 660, I believe. Okay, so we are asked in this one to write the equation of the best fit line. So let's do that on both the graphing calculator. So the graphing calculator, we can add a calculator page. We can choose menu, statistics, number 1, number 4, linear regression. We can choose our X, choose our Y. We can click OK. Now again, Desmos is allowed on the AP exam this year. So if you want to try Desmos, try a combination of both the calculator and Desmos. You're welcome to do that. For my online students, I apologize. I didn't get Desmos going for my online students this year. I'm finding some good success with my students at Washington, so I am trying to incorporate it a little bit. At least you have that advantage that you can use both, because we'll use Blue Book on the AP exam this year, and there's a Desmos calculator built in. But anyway, here we've got the equation. It's right there, a plus bx, so it's 210 plus 11. Let's remember to write it in context. So it would be predicted calories, whether you put the word predicted or you leave off that word and you throw on the hat. Predicted calories equals 210.95 plus 11.05 times the fat. Okay, if you are using Desmos, Desmos is a little bit more intuitive. It's a little easier. Again, once you type it in, if this blue button is on, it's graphed it, but we can't see it. So you find the zoom button, and it'll zoom in. It'll find that value for you. It should look like that. If we're graphing it on the Inspire calculator, you of course can use the data and statistics page, put X on the bottom, Y over here, and we see the same thing. It's a little bit nicer a graph on the Inspire calculator, a little bit less. Here you might have to zoom in to see some of your numbers a little bit more, but you can adjust that both here or in with the graph settings, and you can move that in and out and sure can drag things around and still get the good picture on here. But then up here on the Inspire, you can add the regression, and it puts the regression, and we have Y equals, now you have to remember to replace Y with predicted calories. And the one thing I don't like about Desmos, it puts it in MX plus B form rather than the A plus BX. It's still A is 210 and B is 11.05. So we get the same equation there, and it's right there. Okay, now let's take this and let's see if you remember how to explain R squared. Now you have to memorize that sentence. You may have to look back in your notes. I would encourage you at this point to pause the video, look back in your notes, do that if necessary. And I'm going to move on. Let's remember, if you did look back in your notes, you found this. This percent of the variation in Y is explained by X. That's what you have to memorize. So some percent of the variation in calories is explained by the fat. Well, what's that percent? It's 92% of the variation in calories is explained by the fat. And where do we get that? On the Inspire, you're going to find that on this page, 92%. On the Desmos, you're going to find it. It's on the same thing. What I do like about Desmos is all the equation, the graph, it's all right there on the same screen. So that's an advantage. Okay. So next, residuals. What are residuals? This is new. So a residual is the observed value, which is a point. Okay. It's one of the points. Subtract the expected value, which is the line. So our book, which I don't really go to the book. I don't even know if you have a physical copy of the book. You all, of course, have a copy of the book in the My Math Lab that you can read. So you can read the actual textbook there, and it's E, which is the residual. E stands for error. It's not a mistake, by the way. It's something unexplained. When we look at this, we have a point. This point is the y value. It's the height, and we subtract the y value of the line. So it's y minus y hat. So this one would result in a positive residual. It's above the line. This one, a negative residual, because the y value is shorter than what the line is. Okay, these are the equations. It's also the residual is the observed minus the predicted, or observed minus expected. The expected is the best fit line. So again, a positive residual is above the line. All these points that are above, if you draw straight up, that's going to be a positive residual, positive residual, positive residual, negative, so on and so forth. Those are all going to be positive or negative residuals, depending if they're above or below the line. Now, we talked about this on video 1. LSRL means least squares regression line. It's the same thing as saying, what's the best fit line? What is the line of best fit? What is the linear regression equation? All those things mean the same thing. But if you do see LSRL, why do we call it LSRL? Because when you draw in all the residuals, every single residual, if I draw to this dot and then I make a square, the best fit line makes the sum of all these squares, and we would get all these squares. It makes them as small as possible. Now, I don't know if I can even do this on on Desmos. I haven't even looked at that. I don't think I can. So I'm not going to try, because I'll just make a fool of myself trying to guess at it and waste time. But on here I can. On this one, I can go Menu, 4, Analyze the Graph, go number 6, and then show the linear regression. So if you have the Inspire, go ahead and do that. Then let's go Menu 4, 7, 2, show the residual plot. So there's the residual plot. Now up top here, I'm going to go Menu 4, 7, 1. I'm going to show the residual squares. And you see all these little squares. It tells me the sum of squares is 3,735. That's the smallest it would be, because if that's the best fit line, I can't get those squares, the sum of those squares, any smaller. If I were to take this line and I were to draw the line through here, you see this square would be much bigger. It would make it a lot bigger because it's not the best fit line. So it makes the sum of those squares as small as possible. Now, if you did that, hit a Control Escape. Let's get those squares off there. We'll leave this residual plot up because we are going to talk about that a little bit later. Again, okay, I'll go ahead and try to make the fool of myself, but I don't believe you can do this on Desmos. We can click this that says plot, and we can put that plot on there, and we'll talk about that residual plot. So if you are using Desmos, go ahead and put that plot on there. You'll see this plot. We can zoom in a little bit. This plot looks basically the same, should look the same as this plot here. Okay, looks the same. All right, but I can't get those residual squares on there. At least I don't know how at this point. There's probably a way, but it's probably way too complicated for what it's worth on Desmos. There are about 3 different functions I found, and this is probably one of them. I did not research this one, and that's okay, because we don't have to know the residual squares. What we have to know is if we see LSRL, that means least squares regression line. That means best fit line. Okay, and that's all you really need to know about that. Okay, now we're going to answer the question today, is a linear model a good model? To be a good model, what you want is you want randomized residuals. And we'll talk about why. I've got a little story about Andre the Giant, if you've never heard about him, if you ever watched the movie Princess Bride. Does anybody want a peanut? Then you know what I'm talking about. And if you don't, then so be it. All right, randomized residuals indicate a good model. Curves or patterns in the residuals, bad model. So random residuals, good model. Curves or pattern, poor models. So here, these are 6 different residual plots. I want you to look. Do they appear randomly scattered above and below the line, or do they appear in some sort of a curvy pattern? Then you know if it's a good model or a poor model. So just take a moment, go through those 6. Should only take about 30 seconds to say good model, bad model, and that's all you're doing. So here we go. Should have come up with, pause it if you're not done. Poor model. See, this one's curvy, right? This one seems random, so that's a good model. This one I would say is probably a fairly good model. It's random. Yeah, I can see a little bit of a curve, but overall it's random above and below. So I would go with that one being good. This one is definitely curved, so that's poor. This one is definitely curved, so that's poor. And this one seems fairly random, so that's good. So we have 3 goods, 3 bads. These are the 3 that I would say are bad. These are the 3 I would say are good. I don't know why I have that scribbled out there. That's good. Okay. Yeah, I see the curve that kind of everybody sees there, but it's not curving above and below the line. So even though it's a little bit thinner in here, and we'll talk about that as we go to. So your fat versus calories is still in the calculator. And if you look, what would we say about this? There's one point over here that's an outlier. I mean, it's far away from the rest. So let's just look at these 6. Are they randomly patterned above and below the line? So if we said, is this a good model, yes or no? I would say with the fat versus calories, yes, because the residuals appear random. And then you should make a sketch on your test if I ask that question. Over here, you can get the same thing. You can zoom in a little bit. Yep, we got that outlier, but it's randomly patterned above and below the line for the residuals on Desmos, so that is a good model. Okay, so we've got another set of data. Let's go ahead and put those in, 2, 4, 6, 8, 10, 12, 14. So I'm going to go ahead and try to do it quickly in both. I do not have them in there. So I'm going to call this one AABB. So let's get a graph. Again, let's graph X versus Y. Okay, looks, not X versus Y, AA versus BB. I was like, that's the same thing. Okay, so that's a graph. Now, what I see is, first of all, I don't think that's a line. It looks very curved, and the residual plot is going to emphasize that. So on the Inspire, you go menu 4, 6, 2. You have to get the graph on there first. Then you go menu 4, 7, 2 to show the residual plot. And see, this has a clear curve in the residual plot. So if I'm answering, is a linear model appropriate, or is a linear model a good model? Same question, just worded in a different way. I have, my answer is a linear model is not. It's a bad model because the residual plot is curved. Now, if you're still writing that stuff down, you can pause the video as needed. But I'm going to go ahead and put this in quickly into Desmos as well, because I do think there's an advantage to using Desmos. Again, if you haven't used Desmos, you click the X here. You can just X out of stuff. Go back into the table, and we're going to type these in. I think it was 2, 4, 6, 8, 10, 12, 14 were my numbers. And then Cannot see my, can't see my mouse. Boy, where in the world is my mouse? There it is. If you saw it, you were laughing at me. 0.2, 0.5135. And 1220. All right, so again, the graph is on, so I'm just going to add the regression. Then I'm going to click down here. It says add the residual plot. And it's very intuitive as Desmos. It just kind of does those things. And then I'm going to click my zoom feature just to get everything on here. Now what I might do with my residual plot, this one is kind of confusing. I might shut off my initial graph so I don't confuse my residual points. So you can shut the residuals off. You can put the original points back on. There's my original graph. It looks curved. I can shut these off and put on my residuals. I want to focus in on the residuals, so that residual plot is definitely curved. If I make a sketch of it, I would say on this one, again, make a sketch, and a sketch is not accurate. You just go, here's a line, make a little curve through there. And a linear model is a poor model because the residual plot is curved, or the residual plot does not appear random. Same thing. You then have the idea, I shouldn't use a line because I got a bad residual plot. What do I do about that? I go to chapter 9. Okay, we'll learn about that in chapter 9. Okay, now why is a residual plot a good model? There was a guy years ago, his name was Andre the Giant. He was a professional wrestler. If you've never heard about him, Andre the Giant had gargantuan syndrome. He kept growing his whole life. Okay, so Andre the Giant, here's the thing. When they do surgery, many times one of the factors they take into account in surgery is weight. Well, Andre the Giant weighed about 550 pounds. He had a bad back and he needed back surgery. So with the weight, they try to use a person's weight as one of the factors. They have other factors and things that they have to predict how much anesthesia to give him. Well, they didn't have any data on any person that big because, they had data on people down maybe at 100 pounds up to maybe 300 some pounds, but 550 was way out of there. It's what we call an extrapolation. It was a prediction beyond any data they had. And what they were scared of is they're scared of first of all, giving him too much anesthesia could kill him. And then they're also scared of giving him too little and have a disoriented giant because he was an immensely strong human being, a disoriented giant, not knowing what's going on and hurting others. So what they did is they asked him, now I don't want you to get any, I'm just going to tell you this story. Okay, so they asked him, how much alcohol does he drink in order to get slightly inebriated? And what he told them is usually it's about a 2 liter. Now this isn't 2 liters. This isn't even close. Picture the big 2 liter bottles. A 2 liter bottle of pure vodka before he started to get slightly inebriated. And they looked at him and they said, you've got to be kidding. So they asked some of his friends and they said, yeah, that's about right. So, I mean, he was a big human and he could consume a lot of alcohol. So they factored that in there with this. They did what's called a multivariate regression. But understand, when they did this, they wanted to have random residuals, and I want to explain why. So if they're trying to predict his anesthesia and they have this, they have residuals that are curved, okay? So if it follows this pattern and they predict out here, this is the amount of anesthesia they're going to give him, but what they really should give him follows this. So when they predict out here, they give him this much anesthesia, they should have given him this much anesthesia. Well, they give him too little because this is what they predict to give him. They give him that, it's too little, he wakes up on the operating table, he hurts somebody. If the residuals were patterned this way, and they're supposed to give him this amount, they give him this much, it's way more because the line is way more than what they should have given him. This line represents what they should give him. Then they end up harming Andre the Giant, possibly killing him because they gave him too much anesthesia. But when you have random residuals, the theory then is when you make a prediction out here, because it's random, you're only going to be a little bit off. So yeah, maybe it should have been this much, maybe it should have been this much, but you're going to be in the ballpark. It is the reason why they have an anesthetist, a doctor who does anesthesia on their monitoring vitals and making sure that things are going okay, not giving too much, and we understand that as well. But that's the story, and hopefully that sticks with you, why they should give, why we should have random residuals. There can be some effects for that. So next, is a linear model appropriate? Pause the video. I'd like you to put these into your calculator and see if you've got random residuals. Again, I'll put them in. We've got 1 through 10. I'm going to go ahead and put these in Desmos. Okay, I've got them in. I'm going to go ahead and I'm going to add a regression. Then I'm going to add the residual plot. I'm going to shut my regression off and look at my residuals. I'll zoom in a little bit and just see, is it an appropriate model? It looks pretty random to me. So again, if you're doing the Inspire, put them in, graph them. I graphed A and B here, and I went menu 462. You got to get the line on there first. Then menu 472, and sure looks like it's random. So I would say yes, it's a good model. A linear model is a good model because the residual plot appears random. Make sure you make a little sketch. No accuracy to a sketch. You just put it on there, and away you go. Now, there's another indication of poor models. You can have a residual plot that changes in variance or thickens. So like at one end, it gets thicker than the other, whether it's this end or whether it's that end. That also can indicate a good model. A good book, the plot thickens, but a residual plot, if the plot thickens, it's not so good. All right. All right. So does the plot thicken? Again, that makes for a good book. Here, thickens, so those would be poor residual plots. Just going to note this. One year I just didn't mention this, and then it happened to be on the AP test. And SE, if you see SE, it's one of the formulas that we have on the formula sheet. SE just means it's the standard deviation of the residuals. One year there was a question, what is SE on this chart? And all students had to put is it's a standard deviation of the residuals. There might be a question. I used to have one on there on the My Math Lab, but I don't think I have that one on there. Anyway, we will end that for today and call that good. Thanks for watching this video.